Hi, chemistry. I guess I'm making this in the afternoon, so good afternoon. I never get to say that to you guys. So what you are seeing in front of you right now is a copy of the notes that we're going to take. I'm just going to make myself a little bigger while I talk, and then it'll be a little smaller when we start notes. But you just finished a stoichiometry quiz. That was essentially the end to our unit 4, and you guys did okay. I understand that there's a pandemic happening, and so we can't really study the way that we want to. I also understand that it is a Google form, and we've never taken a quiz on Google form before. So considering, I think that the system worked out decently. There's going to be a couple fixes. But that being said, welcome to your Unit 5 Acids and Bases Chemistry Notes. We are moving forward. Now, just because this is a brand new unit, again, doesn't mean that you get to forget everything that you learned in the past year. But more specifically, you cannot forget what you've done in stoichiometry. So that last unit, we're essentially just adding another layer onto the stoichiometry unit. So a couple things before we get started. The first thing is that this is going to be a lot of notes, and so there's a couple ways that you can take them. You can either have your notebook right in front of you, like I do here, and take notes that way. Pause the video, play the video, rewind, do what you need to do, and copy the notes down on your notebook, just like you've been doing for the entire year. I highly suggest that that's the method that you choose to do. You've been doing that all year. You've been taking notes that way for this entire year. So I think it'll be beneficial. It's also beneficial, and studies have shown that if you write down information, it gets stored in your long-term memory in a different way. And so it'll help you remember and it'll help you engage with the material a little bit more. And that's all we're asking for as teachers is engagement. The second way that you can do this is I've also posted this PDF on Google Classroom, so you can always look at that, either print it out, make sure it gets somewhere that you can read it and flip through as you're taking a quiz, perhaps. I don't care if you use your materials on your quiz or not from moving on forward. So if you want to be able to have this in front of you, I highly have these notes in front of you. I suggest that you either print out a copy of this, watch this video, and maybe make a couple notes off to the side, or you write it down in your own spiral. I miss all your faces. I'm going to apologize because normally when we do these lecture notes, you get to ask me questions. I get to ask you questions, and it's a little more interactive. Today is just me talking at you. And it's also a lot of notes because I'm cramming essentially 2 days worth of notes into one video. But it's going to be spread out throughout the whole week. So it's 2 days worth of notes. Buckle up because it's a fantastic topic. I love it. Shrink me now. Okay, so we are starting with Unit 5, Acids and Bases Chemistry. This is just kind of an extension of stoichiometry and what that does. So before we can start talking about stoichiometry, before we can start talking about acids and bases, we need to first talk about this thing called molarity. Molarity is just another way of describing concentration. The reason we need to be able to describe concentration and mathematically represent concentration is because the chemistry that we would have been doing in acids and bases all involve solutions. Solutions are when you take, we'll just say table salt. In order to make salt water, which is a solution, I would need to put table salt, which is the solute or the thing that is dissolved in a solvent. We would take water, which is our solvent. We'd mix them together. The salt would dissolve, and then we would have a solution of salt water. But knowing that, we'd be able to calculate the number of moles per liter of solution, and that would be our concentration. So we need to be able to have a way to represent concentration here. And we do. It's using molarity. So molarity is equal to our moles of solute, which is in the units of mole, per liters of solution. So solution is your solute dissolved in whatever your solvent is, which is water 95% of the time. A couple ways we can represent this. When we want the concentration of something, we would use brackets to represent concentration. Capital M equals molarity. Molarity is also in units of moles per liter. Okay, so the best way that we can kind of get used to using molarity is just by doing practice problems. So you'll see we have an example number 1 here. This is labeled example 1 so that if you have questions, why did you box the example 1 in orange? I'll be able to go to example 1, reference my notes, and be able to give you a quick answer. Okay, so try and reference these if you have questions. So example 1 wants us to calculate the molarity of a solution prepared by dissolving 9.8 moles of solid NaOH in enough water to make 3.62 liters of solution. So we need to find the molarity. Like any problem, I'm going to start with underlining all the things that I know, circling the things that I'm trying to go to or what I'm trying to find. So in my problem, I'm given 9.8 moles of NaOH. I'm also given 3.62 liters of solution. I need to find molarity, or my capital M, or my moles per liter. You are always going to have to kind of unpack molarity. And you're going to have to say, oh, I know that molarity is really moles over liters. Just like when I say molar mass, you know that it's really grams per mole. So looking at this problem, both of my units for my given values are in moles, which I have moles over here, so I don't need to change that. I have liters here. I have liters here. I don't need to change that either. So I can just go straight into my calculation, and that is putting 9.8 moles of NaOH over 3.62 liters of solution. Now, some of you might be looking at this and saying, oh, SOLN, I wonder what that means. That just means solution. It's easier to write SOLN instead of the full word of solution when we're doing problems like this. So I do 9.8 divided by 3.62 in my calculator, and I get 2.7 molar NaOH. That's how we say it, molar, not molarity, not moles, because that's something different. And essentially what this answer is telling us is that if I had 1 liter of this solution instead of 3.62, that I would have 2.7 moles of NaOH in that solution. Helpful, not helpful, I don't know. But this is kind of essentially how we would work with molarity. Let's move on to example number 2. Remember, pause me if you need to. I will just keep going. Okay, example number 2. A student dissolves 152.5 grams of copper 2 chloride in water to make a solution with a final volume of 2.25 liters. What is the molarity of the solution? Okay, so just like we did in the last problem, I'm going to write down the 2 things that I was given and the thing that I'm trying to look for. I was given 152.5 grams of copper 2 chloride. I was also given 2.25 liters of solution. I want to find molarity. Notice how molarity is in moles over liters. Here we put a note. We know the grams of copper 2 chloride, not the moles of copper 2 chloride. So before I can do anything regarding the molarity of my solution, I need to first be able to have moles over liters. So that's what my first step is going to be. I need to be able to convert copper 2 chloride, grams of copper 2 chloride, into moles of copper 2 chloride using the molar mass of copper 2 chloride. The molar mass of copper 2 chloride is 134.446 grams per mole. So let's just do a really quick recap as to how to find your molar mass. In your calculator or your phone, which I'm going to use my phone because that's the easiest to see, you are going to need your periodic table. Hopefully you have one right now. And find copper, which is right there. Copper has a molar mass. Oh, it's mirrored. Copper has a molar mass of 63.546 grams per mole. And I'm going to find chlorine, which you don't need to see, has a molar mass of 35.45 grams per mole. I need to be able to calculate my molar mass when I have 1 copper and 2 chlorines. So on my phone, I'm going to start with copper because that's what I have. Recognize my face? Guess not. Okay, so I'm going to start off with copper, and I know that that's 63.546 grams per mole. So I have that in my calculator here. I'm going to add to it 2 times 35.45. Now, in order to do this, you are going to have to put parentheses. So I'm going to put my parentheses, 35.45 35.45 times 2, close my parentheses. This is what 35.45 times 2 is. And now I'm going to hit enter because I added that to my 63.456. There's my molar mass. Okay, so that's just a quick recap of how to do molar mass. And that's how I ended up with that number here. So I have a gram amount, 152.5 grams of copper 2 chloride. I'm going to convert that to moles. In order to do that, I have grams on top here. I need to flip my molar mass because it is a conversion factor, so I can flip it around. And I'm going to have 134.446 grams of copper 2 chloride on the bottom, 1 mole of copper 2 chloride on the top, grams, they both cancel each other out, which is awesome. And now I'm left with moles of copper 2 chloride. And when I take 152.5, multiply that by 1, divided by this molar mass here, I should get an answer coming out to 1.134 moles of copper 2 chloride. Okay, I have my mole amount. Great. Am I done? No, not done yet, because I still need to find my molarity. My molarity is in moles per liter. I have a mole amount. I have a liter amount that was given to me in the problem. So now I can just plug these two things into the equation for molarity and find it out. So molarity is equal to moles over liters. So that's what I'm going to do. I'm going to put my 1.134 moles of copper 2 chloride on top. I'm going to divide that number by 2.25 liters of solution. Remember, that's what we had in the problem right up here. And when I calculate this out, I'm going to get 0.504 molar copper 2 chloride. Okay, so that just tells me that in 1 liter of solution, I have 0.504 moles of copper 2 chloride. Now, here's when I'd be asking you, do you have any questions? Do you need me to stop? Do you need me to pause? But you can pause me on your own, so I'm just going to keep moving forward on to our third example. Now, our first two examples focused on how to find molarity. Now our next examples are going to focus on how to use molarity to help us. So example number 3, if you have 4.1 moles of glucose and want to make a 0.25 molar solution with it, what will be the final volume of the solution? Okay, so same thing. I'm reading through. I'm given a lot of things. I have to find one thing. I'm given 4.1 moles of glucose. I'm given 0.25 molar solution. I need to know what the final volume should be. So what's cool about molarity is when we unpack that molarity, we'll be able to see that it separates into 0.25 moles over 1 liter. Well, this is a conversion factor, just like our molar mass, just like Avogadro's number, just like 22.4 liters of gas per mole at standard temperature and pressure. All of those are conversion factors. And what we can do with this conversion factor is we can flip it over. Now, why am I so concerned with flipping this conversion and turning it into this? Because when I go to solve for my final volume, I need liters to be on top. And I can do that because molarity is a conversion factor. So 4.1 moles of glucose. My cross and my line. I have a liter on top. I have 0.25 moles on the bottom. Just like with molar mass, how the number, the large number, stays with the grams, the same thing happens with molarity. The number in molarity stays with the moles because we're saying that there's 0.25 moles in 1 liter, or 1 liter has 0.25 moles. Okay, a simple 1 unit conversion, 4.1 multiplied by 1 divided by 0.25, I should get an answer of 16.4 liters of solution. Okay, so what that really means is that if I want 16.4 liters of a 0.25 molar solution of glucose, I need to put in 4.1 moles of glucose and dissolve that into 16.4 liters of water. That's what this problem is telling us. Now, this was pretty lucky because we started with moles and we were going to liters. So we didn't have to do any conversions, which is helpful for us. However, that's not going to be the case for very much longer. Example number 4 has lots of extra steps. Example number 4, how many grams of NaOH do you have to dissolve to make 7.25 milliliters of a 2.5 molar solution? Okay, so I need to go through and I need to figure out what I know. What I do know is that I have 7.25 milliliters right here of a 2.5 molar solution. And I'm trying to find grams of NaOH. So here's the first issue, is that in order to get any information from molarity using my volume, these two units have to be able to cancel each other out. Have to. And we can't do that as they are in this moment. So the first step we need to do is we need to convert milliliters to liters so that they can cancel out the liters in the molarity. That's just our simple divide by 1,000. There's 1,000 milliliters in 1 liter. And so we need to divide. 7.25 milliliters divided by 1,000 milliliters will give us 0.00725 liters. That makes it so we can actually use this with molarity to find our moles of NaOH. Why do we have to find our moles of NaOH, you ask? Well, because we need to know the grams, and there's a really easy conversion to go from moles to grams. But I'm getting ahead of myself. So our second step here is that we need to find the moles of NaOH using 2.5 molar NaOH and the volume that we just calculated here. And so let's use that. I'm using this volume, 0.00725 liters. I'm going to do my cross and my line. I know because I've unpacked molarity up here, I know that I have 2.5 moles over 1 liter. Because I want liters to cancel, I don't have to flip this unit conversion over at all. So I have 2.5 moles on top, 1 liter on the bottom. Both of those liters cancel out. I multiply 0.00725 by 2.5. I divide by 1, which isn't going to change anything. And I should get 0.01825 moles of NaOH. But I'm not done. I am not done at all. I need to find, my answer wants it to be in grams. And so I need to convert from moles to grams, which everyone should be able to know how to do because this is our basic stoichiometry problem, calculating grams of NaOH using the molar mass. I calculated the molar mass of NaOH the same way I calculated the molar mass of copper 2 chloride in the previous problem. You add together the 22.990 from sodium, the 15.999 grams per mole from oxygen, and the 1.008 from hydrogen. Add those all together, and my molar mass should equal 39.997 grams of NaOH per 1 mole of NaOH. Now, I wrote it this way so we could easily see that this was still a conversion factor. And when I take my mole amount, my 0.01825 moles of NaOH, I'm going to multiply this so my moles are on the bottom. I have moles on top here, moles on the bottom here. They cancel each other out. I'm left with grams of NaOH. I multiply these two numbers together. I'll get 0.7299 grams of NaOH. Now, what this number actually tells me is that if I wanted to make a 2.5 molar solution and only needed 7.25 milliliters, I would measure out in my lab, I would measure 0.7299 grams of NaOH, dissolve it in 7.25 milliliters of water, and that would get me this 2.5 molar concentration. So that's what that number actually means. Some of you might have been looking at steps 2 and steps 3 and going, can't I just put this into one long equation? The answer is yes, you absolutely can do that. The reason that I broke it down step by step is because you still need to be able to understand what's happening at every single stage of your long stoichiometry equation. This will help you understand that. But if you are someone who likes to put it all in a row, here is what it looks like. You're starting with 0.00725 liters. You're going to cross out your liters and get to moles of NaOH by using your molarity. So we're at this step here. And then you get to skip what we did right here and just convert straight to grams of NaOH using the molar mass. This still works. Of course it still works. You just have to know why each step is happening. That's where these come in. So you can do it either way you want. It's up to you. All right. So, because we can do this all one long equation, that means we have a brand new roadmap. It's not brand new. We have certain sections of it we know. We're really just adding on to this like teeny tiny little space. But here it is. So we already know molecules and atoms of A can get to moles using Avogadro's number. We know that liters of a gas at standard temperature and pressure, and that is of gas A, can get to moles using 22.4 liters per mole. We know that grams of A can get to moles of A using the molar mass. Now what we know is that liters of solution A can get to moles of A via molarity. Okay, we know that molarity is moles per liter. So we have moles here and liters here. We're using molarity as a conversion factor. We can add this into our roadmap. And of course, what we can do to one side, we can absolutely do to this side. And so I could use molarity B to get from moles of B to liters of solution B. So now we can use molarity as a conversion factor to find moles of A or moles of B and go from there. So there's no limits to this. Sometimes I might stay on this side and say, oh, well, if I have liters of this solution and I know my concentration, I could also figure out how many atoms are in that solution of A. Or I could figure out how many grams of A are in that solution. But I could also go all the way to the other side and know how many atoms of B is in that solution, or how many grams of B, or how many liters of solution B I need. Very helpful. This is your new roadmap. This is what you should be using from this point forward to solve any problems. I'm following along in my own notes. Okay, so let's do an actual stoichiometry problem with molarity that involves using this balanced chemical equation here. This is example number 5, focusing on molarity stoichiometry. So example number 5. It takes 12.5 milliliters of a 0.300 molar solution of hydrochloric acid to neutralize 285 milliliters of sodium hydroxide solution. What is the concentration of NaOH solution? Tough. They didn't give us any balanced chemical equation. They didn't even tell us what the products are going to be. They just gave us 1, 2, 3 numbers and said, find a concentration. So how do we do that? First step, always write down what you know. We know 12.5 milliliters of HCl. We know that that solution had a concentration of 0.300 molar HCl. And we know that that neutralized 285 milliliters of NaOH. And it wants us to find our concentration of NaOH. Now, what's helpful is that when we break apart molarity, or our concentration of NaOH, we know that that's moles of NaOH per liters of solution. Lucky for us, we already have our liters of solution here. So what we really need to calculate is our moles of NaOH. But before we can even do that, we need a balanced chemical equation. Now, you might be able to look at this and go, oh, that's what it says. Whoa. We're just going to keep going. No editing, all bloopers. You might look at this and say, oh, that's what that chemical equation was supposed to be. But you're looking at it. So you should actually be able to read this and say, oh, hydrochloric acid, or HCl, neutralizes NaOH. This is an acid-base neutralization. Acid-base neutralization reactions are a special type of double replacement that produce water and a salt. So if I go down here and I mix hydrochloric acid with sodium hydroxide, and that's going to make water and a salt. And we're lucky in that it's all a 1-to-1 to 1-to-1 ratio. We don't need to do any balancing. Okay, but acid-base neutralization. This is kind of a segue. We're going to talk about these types of reactions and how an acid-base neutralization doesn't always look like this anymore. Whoa. But let's focus on this problem. And that is, we need to be able to find how many moles of NaOH are going to go in this many liters of solution. And in order to do that, we first need to make sure that everything has all the same units so that we can cancel everything out nicely. That means that we need to convert all of our milliliters into liters. And that is just like I showed you back in example 4 or 3. We are dividing this number by 1,000 because there's 1,000 milliliters in 1 liter. You might have already done this in your head and written it up here. That's fine with me, but I wrote it down. And I converted 12.5 to 0.0125 liters, and 285 is converted to 0.285 liters of NaOH. Labels are important here, so make sure you keep those straightforward. Now that we have everything in liters and we can use this as our own little conversion, now we can calculate our moles of NaOH. So you're looking at your roadmap here. I'm going to show it right here so I don't have to scroll all the way back. But you're looking at your roadmap here, and I'm going to go from, oh, this is backwards for me. I'm going to go from liters of A, or liters of HCl, to moles of HCl using molarity, then to moles of NaOH using my balanced chemical equation. So there's my plan. I'm going up, and then I'm ending right here. Okay? So here's my plan. I wrote it down here. Remember, each arrow is its own little step. Ooh, I'm gonna yeah, there we go. Each arrow is its own little step. And so I'm starting with my 0.0125 liters of hydrochloric acid, and I'm going to convert that to moles of hydrochloric acid using my molarity. We did not have to flip the molarity around because liters on top are here, and then liters on the bottom here. They cancel each other out. I'm left with moles of hydrochloric acid. But I don't stop there because this is where I'm at right now. I have to go to moles of NaOH, and even though it's a 1-to-1 ratio, you still need to show your work and show that math. And so you should be able to have a 1 mole of HCl on the bottom because I have moles of HCl up top, and then 1 mole of NaOH up top because that's the unit I'm trying to get to. So all in all, I'm going to take this number, 0.0125. I'm going to multiply it by 0.300, divide by 1, multiply by 1, divide by 1, and I will get 0.0037 moles of NaOH. Okay? Now I found my moles, but I'm not quite done because this problem wants me to find molarity. I have to find the concentration of NaOH. So that brings me down to my 5th step, calculate the concentration of NaOH. Well, we know that molarity is equal to moles over liters. I have a mole amount because that's what I just calculated over here at 0.0037 moles of NaOH. I have my 0.285 liters of NaOH. That was calculated up here and given to me. And I do this number divided by this number, and I get 0.0132 molar NaOH. Now, what this number tells me is that this is the concentration of NaOH in this specific amount of solution. It also tells me that it took this much HCl, this much hydrochloric acid, at this concentration to neutralize this. Now, when I say neutralize, that means it turned into water and a salt. But neutral has its own special meaning. That means there's no more acid and there's no more base, so that this whole reaction just totally went forward. Now, we've been talking about acids and bases a lot, and for the rest of these notes, we're going to be talking about the definitions of acids and bases and what those all mean. So we're done with the tough math right now. Know that there are still going to be practice problems using molarity, but that's not everything that you have to do. We also need to talk about properties of acids and bases. Okay, because we've been talking about acids and bases on and off for the whole year. We need to kind of figure out what those mean. So some properties of acids and bases, you might have heard these before, you might not have. It's okay. I still think you should write them down. Acids, they taste sour. So when you think of sour things, you think of lemons or limes, maybe some oranges, sometimes apples, depends on the apple. That's because they all have different types of acids in them. They neutralize bases. We just saw this in our problem up here, that hydrochloric acid neutralized NaOH to form salt and water. pH, you might know what pH is, and right now we're just going to kind of define it as a way to measure the acidity of a specific acid. So how strong or how weak that acid is. pHs that are lower than 7, that means it's an acid when you test that. pOH is kind of the opposite of what pH is, and it measures the basicity, so how much of a base it is. And the pOH for acids is greater than 7 because acids are not bases. Another cool thing about acids is that they conduct electricity. And they do that because when an acid, like hydrochloric acid here, is dissolved in water, that's what this symbol means, it'll form H plus and Cl minus. Well, the ions conduct electricity. Electricity is essentially free-flowing electrons when in water. So if you dissolve an acid in water, you stick a light bulb in it, the light bulb will turn on. True story. So let's talk about some bases. Bases are kind of the opposite of acids. Where acids taste sour, bases are bitter, and they're chalky. They neutralize acids. Please tell me I didn't just say what I think I said. Whatever. Oh, we're just going to move forward. They neutralize acids. They have pHs of greater than 7, pOH less than 7. So remember, this is measuring how much of an acid it is. And because bases aren't acids, they have pHs of higher than 7. pOH is measuring how much of a base it is. And it has pOH of less than 7 because bases are basic. They also feel pretty soapy and slippery. So common household cleaners feel soapy and slippery because they are bases. They also conduct electricity. So sodium hydroxide is a pretty strong base. When it's dissolved in water, will form ions, Na+, OH-. And it's one of those ions that will conduct electricity and move free-flowing electrons around it. Okay, so those are some common properties of acids and bases. It's important to know them, but we're going to get into the definitions in a second. But let's talk about some common household acids that you'll see every day. We talked about that sour taste. Vinegar is also something that has that sour taste. Vinegar is acetic acid. We write acetic acid. It's a derivative of the acetate ion or your Chiku ion. If you cover up this H right here, you don't look at it, this CH3COO would have a minus charge on it. That's your acetate ion. You put on a hydrogen, which has a plus charge, then it's neutral and you'll have acetic acid. We write it this way, not this way, because this hydrogen is special. And we'll get into why a little bit, but it's considered an acidic hydrogen. When we're writing the formulas for simple acids, the acidic hydrogen stays on the outside. So this hydrogen needs to stay out here because these three hydrogens are doing other things in the compound, and the hydrogen gets to stay outside. Now, lemon juice is citric acid. Citric acid is also in limes, oranges, apples. Apples also have malic acid in them as well. But citric acid, you'll notice C6H8O7, not a simple acid. We wouldn't be able to write it this way. Battery acid, though, which is sulfuric acid, is a simple acid. So this has two hydrogens on the outside that are acidic, and so we write them on the outside. Notice that this is your sulfate ion, just with some hydrogens on it. Some examples of common bases: we have baking soda, which is sodium bicarbonate, NaHCO3. This H is not considered acidic or basic; it's just there. Hard soap or lye, it's sodium hydroxide, NaOH. That OH is kind of a key factor of bases. And then also ammonia, which is in a lot of common household cleaners, is also a base. So let's talk about how I know that. How do I know what's an acid and what's a base? Well, there's two definitions. There's three technically in the chemical community, but we're only going to talk about two of them. The first one is this really traditional model of acids and bases, and that is an Arrhenius acid and base. This is our traditional model. I'm going to scroll all the way down until we get our example. So our traditional model, an Arrhenius acid is something that produces an H plus or hydrogen ion, or an H3O plus, which is considered your hydronium ion, when dissolved in water. Hey, Beaker. So when I dissolve hydrochloric acid in water, you can see this here. Again, this symbol, the H2O on top, just means that we dissolved it in water. Oh, hello. We form an H plus and a Cl minus. When we put HCl in water, this reaction is saying the same thing as this reaction, but there's something happening with the water. So I combine HCl and H2O here. I'll make hydronium. This hydrogen went to this water to make H3O plus and Cl minus. Can you say hi? Hi. Okay, so that's an Arrhenius acid. It's going to produce an H plus. Okay, an Arrhenius base is when we produce an OH minus or a hydroxide ion when dissolved in water. Sodium hydroxide is our best example here. When we dissolve it in water, we get Na plus and OH minus. Example number 6 says identify the acid or base in the following reactions. Whoa. Okay. Here we have H2SO4. It was in our list of common acids, but the way that you would confirm that this was an acid was because of this H plus right there. Okay, it's producing an H plus. That is our definition of an Arrhenius acid up here. B, we have magnesium hydroxide. Magnesium hydroxide, when it breaks into its two ions, has magnesium and hydroxide. Because it has that hydroxide right there, that's our definition of an Arrhenius base. Okay, so there's one kind of key that you can use to determine if something is an acid or a base, but this is a traditional model and it doesn't actually encompass all acids and bases. So these other two scientists kind of came up with a better way to figure out what is an acid or to define what an acid and what a base is. All Arrhenius acids and bases fit under this definition, but there are also some exceptions that lay outside of the Arrhenius acid and base definition that fits within this one. This is the Bronsted-Lowry acids and bases. A Bronsted-Lowry acid is something that donates a proton. A proton is essentially H+. So let's think about that for a second. A hydrogen atom has 1 proton, 1 electron, 0 neutrons. If I get rid of the electron to form an ion, I will just have a proton left over. So just because it's an H+, we consider it a proton. So Bronsted-Lowry acids donate protons. An example is HF or hydrofluoric acid. It is going to give the H+ away. A Bronsted-Lowry base is the thing that accepts the proton or accepts that H+. And a good example, which is an example of a household cleaner, is NH3 or ammonia. So when we mix these two things together, or they go through a neutralization reaction, the hydrofluoric acid here is going to donate this proton to the NH3+, and this NH3+ is going to accept that proton. So what happens when an H+ is removed from a fluorine? Well, it's not just fluorine. It actually turns into the fluoride ion. The fluorine is going to keep the electron that would have been with hydrogen here. Okay, so it's going to keep, thank you, stop it. So it's going to keep its electrons, so we have an F-. Now your NH3 actually gained a positive charge and a hydrogen, so we are going to combine this and make it NH4+. This is your ammonium ion, ammonium. Sometimes substances can act as both an acid and a base. Those things are called amphoteric. Amphoteric substances are substances that can act as both an acid, which is a proton donor, or a base, which is a proton acceptor, depending on the environment. Our best example of an amphoteric substance is water, and the one that we're going to see the most is water. If I put hydrofluoric acid in water, hydrofluoric acid will donate its proton to H2O, and you will make your hydronium ion and an F-. But if you have ammonia in H2O, then you will see that the H2O donates a proton to NH3. And then we make OH- and NH4+. This is amphoteric. It doesn't matter that it is water, it just matters where the water is at the time. Okay, so I think we can establish that water's pretty cool. We need to actually talk about something that happens in chemical reactions that will kind of blow your mind. So we've seen all of these arrows pointing forward for every single reaction. Just scroll down here. And what this arrow means is that, I'm down here, all reactants go to the products in the forward direction, and no products turn into reactants. That is only the case for special types of reactions, like combustion reactions. If we had combustion reactions that went backwards and made the two compounds, that would be very ineffective, especially considering combustion engines. We don't want those products to go back into the reactants. So what actually happens here is we have this double-sided arrow. This double-sided arrow means that a reaction can go both forwards and backwards. Now, this doesn't happen at exactly the same time. What's going to happen is we're going to mix two things together, and it's going to make a product. Now, what's going to happen is that product will actually separate and turn back into reactants. And then, those two reactants will form a product, and then that product will go back into reactants. And it's just this kind of like seesaw of chemical reactions. Now, at one point, this will happen at the exact same time, at the exact same rate for all the molecules. This is called equilibrium. So at equilibrium, products are being made at the same rate that reactants are being made. That means that the reaction going forward is happening at the same rate the reaction going backwards. Same time. So for every product I make a reactant. Okay, let's look at a little example. We're using hydrofluoric acid mixed with ammonia again. In the forward reaction, we see hydrofluoric acid donating a proton to NH3 to make F- and NH4+. That happens. The reverse reaction is NH4+ donating a proton back to F- and making NH3 and HF. That also happens. So this reaction is at equilibrium when every time a proton is donated here to make these two products, a proton is donated here to make these two products. We're going to talk more about what equilibrium means and what it means for our chemical world much later on. But for right now, all you need to know is that reactions can go both forwards and backwards when they're at equilibrium. And that's what this double-sided arrow means. Moving forward, you'll see that this NH4 acted as an acid. It donated a proton, and this F- accepted that proton and acted like a base. But this F- came from an acid. This NH4 came from a base. And so these two things actually have their own special name. The first one is called a conjugate acid. A conjugate acid is a compound formed after a base accepts a proton. The conjugate acid acts as the acid in the reverse reaction. So if we reverse this reaction, we go backwards, NH4+ is donating its proton. That is acting as an acid, but it came from a base. So if I look here, here's my base, NH3. It accepted its proton, and now it's made NH4+. NH4+ is my conjugate acid because if I reverse this reaction going this way, it would donate a proton to F- or the fluoride ion and make HF. NH3 and NH4+ are considered conjugate acid-base pairs. The same thing can be said for hydrofluoric acid and the fluoride ion, and it will make a conjugate base. A conjugate base is a compound formed after an acid donates a proton. The conjugate base acts as the base in the reverse reaction. HF is our acid. When it donates a proton, we are left with F-. That's our conjugate base accepting the proton from NH4+ and making HF again. Hydrofluoric acid and the fluoride ion are also considered conjugate acid-base pairs. So in this reaction, there are two conjugate acid-base pairs. HF and F- is one pair, NH3 and NH4+ are the other pair. So now we're just going to do some practice. We're on the last page. Okay, example 7. Name the conjugate acid-base pairs in the following reactions and identify the acid, A, base, B, conjugate acid, Ca, and conjugate base, Cb. So in our first one, here, we can see HCO3- plus H2O makes H3O+, and CO3 2-. When I'm going through problems like these, I like to make sure that I know what pairs with what. So if I look here, we can kind of already tell since I have the answers, but I'm looking what in my products is going to match this to the fullest. This H, it has to have a carbon, 3 oxygens, maybe a minus charge, maybe not. Okay, so I'm going to go to my first product, which is H3O plus. Has hydrogens, but it has 3 of them. We're dealing with acids and bases, so it wouldn't donate 2, not at this point. It has an oxygen, but doesn't have 3 of them. It has a plus charge, not a minus charge, and there's no carbon in sight, which means most likely this is not going to be the conjugate pair to this compound here. So the other product, let's look at the other product. We have C, we have a carbon, we have 3 oxygens, we have minus charges, but we don't have a hydrogen. So what actually happened here? Well, if I look at this and I look at this, the difference is a hydrogen and a plus charge. So we got more negative, which means HCO3 minus and CO3 2 minus are pairs. Now we just need to decide, is it an acid or is this going to be a base? Well, I determined that this was an acid because in order to go from CO3 minus to CO3 2 minus, I had to donate a hydrogen. And so I donated that hydrogen, and based on the Bronsted-Lowry definition of acids, acids donate protons. And so this is my acid, making this my conjugate base. Now, through process of elimination, I can see that H2O accepted an H plus, made H3O plus, and so this would act as my base, and this is my conjugate acid. Same thing goes for these 2 equations right here. H2PO4 minus, its pairs HPO4 2 minus. You have to look at what's similar, and these 2 things are similar. Again, water acted as our base because that's the kind of environment that it's in. Number 3, HSO4 minus and CO3 2 minus are going to react to form SO4 2 minus and HCO3 minus. Now we've seen CO3 2 before right here, but I'm going to look at HSO4 minus. I see another SO4 2 minus. The difference between them is a hydrogen and a positive charge, which means I had to donate my positive charge here, which makes this my acid and this my conjugate base. CO3 2 minus accepted that proton, accepted the hydrogen to make HCO3 minus. What I want you to pay attention to is that it wasn't just the way that I wrote it. These are reactions that happen in real life. This CO3 2 minus is acting as a base when it's in the reactants. This CO3 2 minus acted as a conjugate base when it was in the products. So it has something to do with the fact that CO3 2 minus really wants protons. Same similarities here with the HCO3 minus acting as a conjugate acid in the products, and the HCO3 minus here acting as the conjugate, or acting as the acid here, donating its protons. Okay. Last example, example 8 is just answering the following. Is hydrofluoric acid and the fluoride ion a conjugate acid-base pair, and why? We say yes. Hydrofluoric acid is an acid and will donate a proton. When hydrofluoric acid donates a proton, you are left with F minus. So this is kind of your key sentence here, is that if I think, oh, if I donated a proton, would it turn into this? Yes. You can also do the same thing with bases. Well, if I accepted a proton, would it turn into this? No, it wouldn't. So it's not so this isn't a base. But if I donated a proton, it would turn into this. So that's an acid-base pair. B, what is the conjugate base of HClO4? If I'm looking for a conjugate base, that means HClO4 is an acid, and it's going to donate a proton in order to make a conjugate base. And so I just need to get rid of both a hydrogen and a plus charge. That's what we need to remember here. I have Cl4 minus. Same process here. What is the conjugate acid of H2PO4 minus? If I'm making a conjugate acid, I have to start with a base, making this a base. I'm going to accept a proton and make H3PO4. And that is the very end of our 8 pages of notes. You got lots of things in there. You got them, what molarity is and what concentration is. You did a little bit of molarity stoichiometry. Look for that in your practice problems. Use my notes as examples if you need them. We talked about this weird concept of forwards and backwards reactions. We also talked about properties of acids and bases, Arrhenius acids and bases definitions, and Bronsted-Lowry acids and bases definitions. We also talked about what amphoteric means, and we also talked about conjugate acid-base pairs. So I want you to be able to focus on Focus on taking these notes, interact with these notes. If you have questions for me, office hours are on Wednesdays from 10 to 11 a.m. Make sure you're doing those assignments. Ask me questions when you have them. I don't want to see the questions like, I don't know what to do. I don't get this. I need help. I love the I need help question. But what I really want you to do is say, I don't understand why you put this here. Why did you do this? Why did you do that? Why are you giving us 8 pages of notes? Good question. I'll be able to answer it. Come into my office hours, ask me questions. If you're worried about other people being there, don't. I'm sure they would benefit from listening to your questions anyways. Send me emails. That is it. I love you all. Make wonderful choices. I'm sad that I don't get to see your face. Unfortunately, you have to see my face this whole time. But hang in there, wash your hands, stay healthy.